In the last video, I covered specific heat for ideal gas. Remember, that was CP and CV. What I want to do in this next video, which will be much shorter, is talking about the definition of specific heat for certain liquids and definitely solids. And it's a little bit of a subset of what you cover in this class, but some of your homework problems, a small proportion of your homework problems will involve this approach with specific heat. So let's get started. Okay, so this is switching gears a little bit from specific heat for ideal gases. And now in this part, I'd like to talk about specific heat, the way you're going to deal with specific heat. Same basic definition, but how you're going to deal with specific heat for solids and certain liquids. And now the why. Why are you interested? Why would you be using specific heat? Well, the reason is that you're going to be interested in quantifying delta U and or delta H for solids and compressed liquids. So remember that liquid. So, well, let's look at the example first. Here's just a piece of steel, right? So why would you be interested in calculating the change in internal energy of a piece of steel? Well, probably here's why, right? A manufacturing process where you've got a cold piece of steel, and if you maybe need to heat treat that piece of steel and get it way up high, that would be sort of an example of a process which you would analyze as an engineer. Now, okay, so next would be what's in this beaker? Well, water is in that beaker. And now let's think about what you've covered in chapter 3 so far. How would you characterize the phase of those two situations? The water's not boiling. It starts out cold or cool, okay, and ends up hot, not to the boiling point yet, just hot. And so how would you what would the phase of that material, that substance be inside that beaker? Well, it would be a compressed liquid, right? So in thermo, we don't just call it a liquid, we call it a compressed liquid. And so I think you get the idea of there can be situations, kind of like the first law for a closed system, where you need to find delta little u, and of course, then why are you doing that? Because you need to find delta capital U, the mass times the change in little internal energy, and you're using that in the first law for a closed system. And later on, for open systems, you're going to be dealing with enthalpy changes, H2 minus H1. So that's why you're looking for delta U. And so I'm going to talk about how you can use specific heat for these substances here. Okay, so I'm not getting off track. I've got a reason for presenting this. And you making engineering problem decisions, let's see, in the here and now, you need to make problem decisions when you're reading your homework problems and coming up with a solution. A little higher stakes, you've got a quiz or a test or an exam. You've got to read the words of a problem. Hopefully you'll start with a sketch, but you've got to make some decisions on where do you go from here? So this is what we don't want. We don't want your hair to stand on end when you've read a problem in a quiz or a test or exam and say, I just don't know what to do, right? So we don't want that. And so I want to review with you, just give you some tips on what kind of decisions do you have to make and in what order when you read a problem and then you set out to solve the problem. This is true for more than homeworks, quizzes, and tests. I mean, this is the very indicative of what you do as a practicing engineer as well, of course. But in a lot of ways, when you're a practicing engineer, you're seeing the problems with your own eyes. You're not always assigned a problem. You're seeing problems that you want to go out and solve on your own proactively. You're not just assigned things to do. All right. So you see a problem or you're assigned a problem. What do you do? Well, first question you ask yourself is this an open system or a closed system? You've got that nailed, right? And then once you've answered that question, because you start planning your work. If I've got an open system or a closed system, then you say, well, what kind of substance am I dealing with? Wow. And so in chapter 3, we're near the end. We're at the end of chapter 3. What's my substance? And so basically, I've either got a phase change substance like boiling water, superheated vapor, saturated vapor, or I have an ideal gas like air or nitrogen or CO2. You get the idea. And then rarely or from time to time, depending on your role or depending on your homework problem, quiz problem, you may be faced with analyzing a solid or a compressed liquid that stays in the compressed liquid phase, kind of like that heating water in a beaker that's just going from one compressed liquid state to another compressed liquid state. Okay, so that's the idea. And so I just checked here a few minutes ago on my Jay's Toolbox YouTube channel. Under the fundamentals playlist, thermodynamics fundamentals, I see a 32-minute video called Decision Trees. And in that 32 minutes, instead of doing definitions and dragging you through definitions, I try to put it all together and try to help give you some tips on how do you make engineering decisions when you're just faced with a problem, not stepping you through the textbook on the textbook material. So suggest you might want to browse that. It's 32 minutes. It would probably take you less if you want to jump ahead, jump back, all that idea. So let me suggest you go find Thermodynamics Fundamentals playlist Decision Trees. Okay, so now the topic of our specific heat for solids and compressed liquids. Now, what are these two things? What do these two substances have in common? What do these have in common? They're both a steel rod, a solid, a brick, okay, and over here, compressed liquid, a bucket of water that you heat up a little bit, okay. Both are considered incompressible substances. So try get in your mind. You've got a vision of what a steel bar looks like. Get in your mind what a compressed liquid looks like relative to the PV diagram that you've gotten very good at visualizing in your head. Okay, both of these are considered incompressible substances. Okay, so quantifying delta U and delta H for, now let's talk about compressed liquids. Okay, you're going to find that there's two methods for determining delta U and or delta H for a process that looks like this, going from one compressed liquid state to another compressed liquid state. There's two methods, okay? And so the first method, I hope, comes to your mind from previous chapter 3 work, and that is we covered that for compressed liquids, it turns out the internal energy is a function of temperature only for compressed liquid, and you evaluate U1 you go to your temperature table, look up U sub F, that would be the internal energy of saturated liquid, and you write that down, and that's U1. And you do the same drill for U2 at state 2. You know T2, you simply go and look up UF at T2, and that enables you to find delta U. Okay, look, that's what you got to stick with. That's what you need to stick with in thermo class because you've taught yourself to do that for this situation. So I strongly recommend you stick with that method in your thermo class. Now moving ahead to junior year, ME 3304 is your heat transfer class. Well, let's not get too ahead of ourselves, but you're going to use a different method for determining delta U and or delta H for going from cold water to hot water or cold lubricating oil to hot lubricating oil. Okay. You're going to use the specific heat method. And that's what this video is all about. So the specific heat method, it's a different method for calculating delta U and delta H for for solids and these type of liquid problems where you're not changing your phase. You're staying in the compressed liquid phase, whether it's water or lubricating oil or glycol, things like that. All right. I hope that helps. I'm trying to keep it simple for you. So in your thermo class, this is the way you need to stick with evaluating U2 minus U1 for compressed liquids. Use your steam tables for saturated liquids. Okay, check. Okay, now we're moving to section 310 back in your textbook. And it's incompressible substance models. And this has to do with using C sub P and C sub V for compressed liquids and solids. So now think about the steel bar and the beaker of warming up water. Okay, so you got to read this section. You don't have to dissect it, browse it, because I'm trying to provide you with the bottom line. Okay, so here's the bottom line. It says that U2 minus U1 for incompressible substances, the change in internal energy is a function of temperature only, and it's related simply by some constant C, and this is called the specific heat. So this little C here in your textbook, equation 320, that's called the specific heat. Oh my God. So now you got a third thing that's called specific heat. Okay, so now you're really confused, right? So what's C sub P? What's C sub V? What's C? Let me go to the big reveal. The big reveal is that, so remember the definition of CP and CV, basic definition for any substance. It's a partial derivative. Then in the last video, we talked about ideal gases. Okay, substance, ideal gases. And so we showed that this partial derivative definition goes into an ordinary definition. And I spent 40 minutes talking about how do you get delta U if you have CV. It might be constant, it might be variable, blah, 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 blah. Just about put you to sleep, but hopefully it shows you how to get to a numerical result. All right. For this, it turns out for incompressible substances, so that would be solids and compressed liquids. So for solids and liquids only, it turns out that CP equals CV. So notice here it says incompressible. So that's solids and liquids that for our modeling. CP equals CV, and that equals this little C in your textbook. Okay, whew. So I've gotten kind of to the big reveal, but so don't use this as a formula, right? Because this only applies to solids and liquids. So that it's really important to get these things in your mind of the decision tree idea is not blindly using formulas in your book. Because just imagine if you had a chapter 3 problem and you found, oh, here's equation 317. It says CP equals CV. Great. And on and on and on. So you see how you can go down a rabbit hole that is the wrong rabbit hole, and that's going to be the no credit rabbit hole, right? No partial credit, because you'll report back to your instructor if you want to go see if you can get quote unquote more points. Oh, well, I found equation 317, and that's what got me off track. That doesn't cut it, right? Okay. So CP equals CV equals C, specific heat, only for solids and compressed liquids. Boy, I started lecturing there, didn't I? Yikes, it's almost like I'm teaching class again. How do you get C for liquids and solids? It's very interesting. Let's go to table A19. Now, what you do is you go to table A19, and it's a single page, and it's a long list of solids up high, and then some liquids down below. And let's look at the column heading. It's very interesting. Table A19, it says specific heat C sub P. All right. Well, you've got to be savvy enough to know the textbook material to see that C sub P for this list of substances, CP equals CV equals just the constant C. Okay. So that's the big takeaway. Okay, that's the big takeaway, is that you may have a homework problem or two where you're heating a brick or you're doing something with an oil, lubricating oil, or some type of quenching oil, something like that, or copper, a copper block. I can think of a classic homework problem where you're cooling a copper block in a bath of quenching oil. This classic case of a solid and a liquid that's simply heating up. All right, you get the idea. And so, oh, and one thing I didn't even include a slide on. Okay, once you've got C, we're here the recap. Once you've got C, what do you do? Okay, yay, you've got C. Well, you're trying to find delta U. You've got a copper block. It is a closed system. It's cooling down. Okay, well, you're going to use the first law, and you're maybe looking for heat transfer, the heat that it transfers into the oil. I need delta U. If I know the mass of the block, delta little u for the copper block would be C times delta T of the block. Pretty simple, right? So I didn't even put a slide in for that. Okay, so what's the takeaway for this short video? Cp equals Cv equals C for solids and liquids. Both are considered incompressible substances. The preferred method for determining delta U and delta H for water in ME 2034, your class, is property evaluation at F. Okay. So you get the idea. If you've got for solids, you're going to go to table A19 and look up C, even though it's tabulated as C sub P. That's just C for solids. And so that's going to be your lookup. Okay, that amazingly, that little short blurb on solids and compressed liquids brings me to the end of the material I wanted to cover for you in chapter 3. And so chapter 3 was such a big and important chapter. I've got one last video where we're going to reprise or sort of recap the entire chapter so that you can move ahead into chapter 4. I'll give you some ideas on that in the next video.